Hello, and thank you for joining us for the Nancy and Bill Norton Patient Educational Series event, The Gut Microbiome, Its Overall Health and Illness. Today, we'll be going through quite a few GI illnesses and the microbiome and how it's related to your digestive health. My name is Cecile Ricker. I'm the President and Executive Director for the International Foundation for Gastrointestinal Disorders, and we are thrilled that you are able to join with us today. This program, in conjunction with Cedars-Sinai Medical Center, is made possible through the financial contributions from 3 industry partners, Salix Pharmaceuticals, Nestle Health Science, and Gemelli Biotech. Without their support, we would not have been able to put this program on for you today. Thank you for joining us, and we hope that you enjoy this session.
Thank you for putting this together. This is a fantastic conference with a great lineup of speakers that we're going to talk about how the digestive disease tract works and how microbiome works, and further on how microbiome is assessed. Later on, we're going to talk about what diseases are caused by microbiome, and microbiome is involved in what diseases and how can you diagnose them, treat them, and what can you do not to get them if you have gotten them before. So enjoy the speakers and their talks.
Thank you. Haley McCorkle, there she is in the back of the room. Thank you, Haley, for putting this meeting together. We really appreciate all of her hard work, but we couldn't be here today if it wasn't for the companies that actually gave the financial support to pay for what we're doing here today. And those supporters are Salix Pharmaceuticals, Nestle Health Science, and Gemelli Biotech. And we do want to thank them and acknowledge their support today. So before I turn the program over to our program director, Dr. Rezaie, I do want to make a few notes. And one is that IFFGD, or International Foundation for Gastrointestinal Disorders, is a nonprofit organization for patients with GI illness. As such, we do have some board-mandated policies, and one of which is we do not market or promote any products. So we are here just to provide you with education about your digestive health, and also about ways for diagnostics and therapeutics. But we are not promoting any, and we ask during our question and answer time that you do not as well, just from a legal standing for the nonprofit organization, not endorsing any products. Also, please remember during questions and answers, we have these great physicians here who really want to help you, but they cannot answer personal health questions. That's against HIPAA, and we don't want any of them to get in trouble. So please make sure that your questions are generic and something that will be beneficial for the entire group. We are recording our meeting today, and we appreciate all those at home who are watching this on YouTube at the YouTube premiere, and appreciate you tuning in, and they will be very excited to hear your questions as well. So please make sure that you keep those coming during the Q&A. And without further ado, I want to introduce Dr. Ali Rezaie, who is a really, really great friend to IFFGD. He is actually a member of several of our program committees and helps to run our junior academician program. He has put together an amazing program for you today. He works at Cedars-Sinai and runs the Motility Center. He is going to tell you a little bit more about MAST and what they do, and then introduce all of our speakers along the day. So, Ali, thank you for coming and putting this together.
No problem. Thank you, everyone. So, first I wanted to thank you for coming, and also the audience that are tuning in. But also I wanted to thank IFFGD for putting this together. For us physicians, to see this happening, for educational programs for patients that are free of charge and complimentary, and with physicians giving topic-based conferences, this doesn't exist anymore. If you are aware that, for example, the pharma companies, device companies and all that, they're not even allowed to interact directly with patients. So the funding for this type of patient education conferences is simply not out there. So it requires a lot of planning, a lot of advocacy from foundations such as IFFGD to put these programs together. So kudos to IFFGD to do this. Also, I want to thank all the speakers to come and give you the great talks that you're going to hear about. and we're going to talk about what we hear, and we're going to have some questions and interactions, and we'll go from there. So what are we doing today? We're going to talk about microbiome. The problem with microbiome is that it's a field that is moving so fast that if you just want to read about it yourself, it's become so confusing. And this is a field that has exploded in the last 20 years. And just to let you know, it's not just you that is confused. A lot of physicians, including us, the field is confusing. It's very complicated. Hopefully the talk today that we start from the basics and then we turn it down a little bit, that will help you to decipher some of the information that you will see about microbiome in the future. We're going to cover the basics of the anatomy of the gut and how the gut works, and then the basics of the gut microbiome by Dr. Mathur, and then how we assess gut microbiome by Dr. Leite. And then we move on by the rest of the speakers. Dr. Pimentel is going to talk about post-infectious irritable bowel syndrome and how infectious gastroenteritis affects the gut. And also Dr. Nasser will talk about small intestinal bacterial overgrowth. Then H. pylori we're going to talk about, and essentially that's a microbiome disease that affects the stomach. Right? Dr. Nasser is going to talk about a microbiome disease that affects the small bowel. And then we're going to talk about C. diff, a disease that affects the colon, right? So microbiome diseases, depending on what bug, what bacteria, what fungi, what virus, affect different parts of the gut. So that's why we talk about the basics of the gut first. Then finally, Coca Yip, our nurse practitioner, where's Coca? Oh, okay. All right. She's actually a doctor and nurse practitioner. So she will talk about the intestinal methanogen overgrowth, that the role of archaea in the gut, and that is a field that is exploding. And that's fascinating. Probably she's single-handedly treated more emo patients than any of us collected here. So very excited to hear her talk. So let's talk about my first talk, and I'm going to start. And I try to keep it fun. This might be basic for many of you, but hopefully you will get some extra points out of it. All right, so the GI tract, right? It's a lumen that goes, as the talk says, all the way from the gum to bum. So mouth, pharynx, and then this the swallowing pipe, your esophagus, and then it connects to the stomach, and then small bowel, which is 20 feet, and then 4 feet of large bowel, and then connects to the anal canal and the anus, right? So that's the lumen, right? And then there are some sort of supporting team here as well. There's salivary glands that produce saliva, and then there is liver, there's gallbladder, there's pancreas, and these organs also support what your GI tract does. So all together we call this digestive disease system. So it's a very complex system, and it's a huge organ. I mean, depending on what Wikipedia page you look at, the biggest organ is skin, and the gut becomes the second biggest organ, if you want to call it an organ, in our body, which makes it very complicated to study, and each segment does what it's supposed to do. But generally speaking, if we want to summarize it and make it simple, what does it do? It does digestion. It digests your food, which we'll go a little bit more into detail. And as we will hear the talks, it harbors gut microbiome. And this is one field that we did not pay attention much in a GI tract, and now it's becoming a big thing to a point that we think a lot of our body function is controlled by gut microbiome. And also detoxifying the toxins that enter in our body, especially through the liver. So whenever you eat, whatever thing that gets absorbed gets through the bloodstream. But that bloodstream, in majority of the gut, goes through the first pass through the liver. And liver essentially filters this, allows some things to go through, detoxifies and gets rid of some of the toxins and pass it through. And that's what we call first pass, and that's why liver is very sensitive to some of the toxin that we take, because it's the first line of defense when it comes after absorption of a toxin. On the other side, it makes sometimes things tricky, right? Some of the medications that we take, liver takes it, neutralizes it, and then it's gone, right? So that's why we have to take some of the medications through intravenous route, right? So we can't take it orally. So it's a very complex system to deal with. And then the immune system. Gut is actually the second biggest immune organ in our body, and that is very important because it helps us with fighting infections, fighting autoimmune disorders, and also it might turn on us and causing autoimmune disorders itself. So now we have gut-directed immune therapies that are helping us fighting some of the diseases that are involved in the gut. But now the cool thing is that these four functions are intertwined. They work together, right? So digestion, obviously whatever you digest affects the gut microbiome, and the other way around. Gut microbiome affects how you digest things, right? And obviously, whatever gut microbiome produces can affect how liver detoxifies things, because those things that bacteria produces, and you're going to hear a lot about it in the next few talks, they can get into the liver and affect the liver as well. And then the immune system. The gut microbiome activates the immune system in the gut, and vice versa. And also what we eat affects the immune system in the gut and also gut microbiome. So all these four things are completely intertwined. All right. So what is digestive process? When we talk about digestive process, essentially, if you had some breakfast, obviously the first part is ingestion, right? Swallowing it and chewing it, and food needs to be propelled throughout the gut. We're going to talk how food gets propelled throughout the gut, but then the mechanical digestion starts. Mechanical digestion is essentially the trituration, the grinding of the food in the stomach and small bowel that breaks down the food. I'm going to have some slides on that as well. And also the chemical and secretory digestion. Chemical can be with acid, for example, in the stomach, that breaks down the compounds. The bile that breaks down the fat. And also the enzymes that chemically digest the food. And then absorption happens, and then eventually what is left needs to be defecated, and we'll get there how it works. So let's talk about a little bit about the basics of your gut. So if you get your gut lumen and you cut it at that point, you'll see generally the same pattern. So at the beginning, there's just the lining of the bowel, where you see here the lining of the mucosa of the bowel, generally one line of cells, and these are very important cells because they're the first point of contact with food and whatever is inside the gut lumen, right? So the junction between these cells are very tight. We call them tight junctions. And the health of these cells are very important, because if they're not tight, then bacteria can go through, inflammatory cells then can come out. Something in layman terms we call it leaky gut, or increased permeability of the gut. So that's a big problem, and there's lots of research that is going through that. Underneath that lining of the bowel, then there is submucosa, right? Submucosa involves some connective tissue disease, some supporting veins and vessels that bring some blood and also take the nutrients back to our body. And then we'll have the muscles. And these muscles, think of it as a snake. There is some circular muscles, and also there is some longitudinal muscles, right? So, and coordination between those two muscles makes this snake move forward. And the same thing happens throughout the gut, from literally esophagus all the way to the end of the colon, right? And outside of this section, there is a layer like foil. So it goes around, and we call it serosa, that it wraps the gut, right? So that contains the gut. And a lot of diseases involve that area that affects the motility of the gut as well. So these four layers, the mucosa, submucosa, the muscle layer, and that wrapping around, these four layers, you can see it in majority of the organs. But it's not the same all throughout. This is the picture under microscope that you see in different parts of the gut. So esophagus is pretty flat and bland, and it's a different type of cell. These are squamous cells, similar to what you have on your skin. But then when you get to the stomach, you see how different it is, right? So now these are cells that produce a lot of acid, they produce a lot of enzymes. And then when you get to the small bowel, now you see these finger-like structures that, if you have had tripes, those are the tiny villi that you can see, and those are these villi that you see underneath. And you can see how nicely they're organized, and they are involved in absorbing food and also producing a lot of enzymes, immunity, harboring a lot of microbiome that you will hear about. And then the large intestine essentially flattens out because it's mostly involved in sucking the water out and keeping the stool a little bit on a dry side, and that's what essentially the colon does. So what this tells you is that you can't expect the microbiome of each segment of the gut to be the same because the lining is not the same and their job is not the same. That's why their diseases that affect these parts of the gut are not the same. So let's go a little bit deeper to go piece by piece down. So swallowing. So think about it, it's a very, very complex phenomenon. There is a lot of stuff going on, right? So there is air going through your nose that constantly goes to the airway, right? And when you're swallowing, you're chewing everything and then you swallow. So the soft palate blocks this area so the air can't go through. If you haven't tried, if you're swallowing, if you want to breathe at that point, it's impossible, right? So you can't do it because soft palate blocks it. And then obviously the airway also gets blocked and the food goes down. So there is like multiple ways here, and each swallowing, multiple nerves have to work together for this phenomenon to happen. So let me show you actually one of the first videos that was ever recorded of swallowing. This video is almost 70 years old. You can tell, huh? Alrighty, so that's the swallowing. So obviously we don't use this amount of radiation these days, but hey, these are the days that they used to check your shoe size with radiation. If you didn't know that, there was X-ray machines in shoe shops to check your shoe size. But anyhow, so you can see how nicely the bolus is going through the swallowing pipe, and it's a very complex phenomenon. But diseases that affects the muscles in the throat, stroke, autoimmune disorders, and multiple other diseases affect this part, and swallowing becomes affected. So that's why we have a whole field of swallowing disorders in medicine. Alrighty, so how does esophagus pushes things forward? Remember that snake using the muscles, right? There is this circular muscles, and then there is a bolus on top, and it pushes things forward, right? So it's dumps things down. So there's some diseases that this phenomenon is gone. So achalasia, right? Esophagus does not move, so you're dependent on the gravity and lubrication of the esophagus for food to slowly just descend into your swallowing pipe to help you digest food. And obviously, the hallmark of those diseases when esophagus is not working is swallowing difficulty, or we call it dysphagia that we see in those diseases. How do we measure it? I brought some gadgets for you that you can go and see, but we use a manometry. It's a catheter that goes through the nose. It has multiple sensors throughout it, and we can measure the pressure. It also has impedance sensors, so if liquid is going around it, it can tell you how the fluid is going through. So this is me when I didn't have beard. I still didn't have much hair, but when you do the manometry, this is how it's done. So you put the catheter in through the esophagus, and this is how it shows up. So on the left side is the pressure index based on millimeter of mercury. So the more red or magenta it is, the higher the pressure, as you can see here. And the more blue it is, the pressure is low. On the right side is actually the anatomical index. This is the upper esophageal sphincter over here, and this is the lower esophageal sphincter at the bottom here. And this is your stomach, and stomach is full of liquid at this point. So when I'm swallowing, the liquid is going through, and esophagus contracts and pushes things forward. And that's the movement that goes through and dumps in everything into the esophagus. And every segment of this phenomenon can be affected by a different disease, and it can present with different sort of symptoms and needs different type of therapy. How about the stomach? Esophagus enters the stomach, and stomach is a little bit special because it has a third layer of muscle around it. It's called oblique muscles. And what it gives the stomach is that the most complex way of contractions. It can go forward, it can go backward, it can go literally sideways, it can titrate, it can move things up and down, and it can sense how things are moving. And that's why it has been so hard to figure out how the electrical activity of the stomach works, as opposed to different parts of the heart that we know how exactly they contract and the electrical activity works. So in the stomach, this part, the top part that sits underneath your ribs, is called fundus, and then this part is called the body, and this is the antrum, and then this part that connects to the small bowel is called pyloric channel. Okay. So right now you had your breakfast, food goes in, depending on how heavy of a food you ate, right? Food goes down, gets pulled into the fundus, and slowly gets fed into the body of the stomach. And the body of the stomach breaks it down, produces a lot of acid, mixes it up, and tries to break it down into almost 1 millimeter pieces. As it makes it to 1 millimeter pieces, it tries to push it towards the small bowel, and pylorus senses it whether it's that small or not. And if it's small, then it gets pushed back into the small bowel. If not, it comes back and it continues to titrate and grind the food. And that's happening in all of you and me, because I just had my breakfast, right? So if I eat something light, right, let's say a little bit of a carbohydrate or a very light bread, it's going to take about half an hour to maximum 1 hour. If I eat heavy, including the sausage, and then add some bacon on top, then it's going to take 4 hours for it to empty. So that's why different type of food have different effect on satiety and also gastric emptying, which is very, very important. So that is called actually the feeding phase. And then when the contents of the stomach enter the small bowel, then the fasting phase starts, that we're going to talk about a little bit more, because that affects the microbiome significantly, and that is that will be in the future talks. So this is the same catheter that I showed you, and you can see that the stomach is contracting. It's faint, but that's what's happening. So stomach, just your heart is beating. But it beats every 20 seconds. 3 times per minute, your stomach is contracting, and that's the basal contractions of your small stomach. And that changes when you're eating, and depending on what you eat, the contraction vigor, all that changes. A few tests that we have to assess this are, for example, the gastric emptying breath test that assesses the emptying of the stomach. There is a radiologic version of this that you can do it in radiology as well, and we watch how much your stomach empties and whether it's slow or too fast. We have a new sort of devices called gastric body mapping that's similar to EKG for the heart. It's the EKG for your stomach, and tells you the electrical disturbances of the stomach. And these are the new gadgets that we have to check whether the stomach is functioning well. The classic problem that we have with the stomach is called gastroparesis, which is the delay in emptying of the stomach, and that's the problem that we have. So how about the next part? The next part is a small bowel. Small bowel is actually 20 feet. It's very long. The surface of it is about a tennis court because it has those tiny villi, and that helps you digest and also absorb a lot of compounds. So we talked about the villi a little bit and how the structures look like. And this is how it looks like in real life. So we do see when we do the endoscopy, we can go, the basic endoscopy, we go to the stomach and we get to the duodenum, which is the first part of the small bowel. Beyond that, it's hard unless we use something called push enteroscopy, and that goes for another 50 centimeters. But if you want to go deeper, options become very limited. We have double balloon enteroscopy, and also we have the capsule endoscopy that I'm going to show it here. I brought one example of it that you can go take a look, and these are the capsules that we swallow, and it goes and takes thousands of pictures, and we watch that video to see any abnormalities. And the pictures look like this. You can see the tiny villi inside. There's some luminal content. That a lot of research that we do is by sucking this luminal content that you see here. And you can see how beautiful and clean is inside the small bowel if it's healthy. It's not like inside the colon that is, well, it's full of poop. But this small bowel stays very clean and neat. This is when we look with this scope and very closely to exactly the same villi. You can see that how nicely they're aligned. And also look at all the beautiful vessels that they come in, take all the nutrients and take it back to your body. So they're all sitting there like a shag carpet that are sitting there. So also in the small bowel, there are the pancreas empties there, and also the liver and also bile produce bile acids that they go into the beginning of your small bowel. That's very important. Why? Because the stomach produces a lot of acid, and we'll see how much acid it produces, and that is caustic to the small bowel. So pancreas's job is to neutralize that acidity. The acidity of the stomach is about 2 or to 1.5. That's the acidity that if you have that acid and you put it on a steel table, it's going to go through that within half an hour. So that acidity, if you once go to the small bowel, then it's trouble. So pancreas's job is to neutralize that acidity within 2 inches of that acid entering the small bowel to a perfect 4.5 to 5, which is quite amazing how pancreas does that. On top of that, pancreas produces other enzymes, and also enzymes that go into our blood, the most famous one being insulin. All right. So how much liquid is produced in our body? A lot. So just for you to have an idea, just our stomach produces 0.5 gallon of acid per day, right? And that acid has a pH of 2, and at the crypt, it's actually a pH of 1.5. So it's a lot of acid that is being produced per day. So also you have to remember it'll take a lot to take all that acid production away. So stomach is very resilient. Obviously, there is a saliva that is being produced. There is pancreatic secretions. And in total, there is 10 liters of fluid that goes, or 2.5 gallons of fluid that goes through our gut every day. Where does it get absorbed? Almost all of it in the small bowel. So the small bowel is the one that absorbs almost 8 liters of it out of 10. Some of it obviously gets excreted in the feces, and a little bit of it gets absorbed in the colon. So the biggest part of our GI tract that absorbs water is small bowel and not the colon. That's why it's sometimes when you have severe constipation, just drinking extra water is not going to do much because the majority of the water is getting absorbed in your small bowel. It's not going to reach your colon. You're just going to drink a lot of water and you're going to urinate more rather than the water reaching the colon. So that's very important. Also, we do measure the contractions of the small bowel, and you will see it here in this picture. We call it migrating motor complexes, right? So remember we talked about the feeding phase of the stomach. After that food enters the small bowel, then you enter the fasting phase. And the fasting phase of the small bowel is like clockwork. And we didn't know about this until almost 30 years ago. Before that, we did not know this. So at the beginning, the small bowel stays silent, and that's for the enzyme to reach that food that is entered the small bowel from the stomach, breaks it down, and then the second phase, which is the longest phase, happens. The second phase is non-propagating contractions of the small bowel that breaks down the food and allows that food to get mixed up with the enzyme and also getting close to those villi to get absorbed and then finally get the nutrients to you. And then every 2 hours, what I would say, something like this, which is the magic in the small bowel happens, the migrating motor complex phase 3, which is the housekeeper wave. So it starts from the beginning of the small bowel, sweeps all through the small bowel, and dumps everything into your colon, the whole 20 feet. And at each segment of the small bowel, it only lasts about 5 to 8 minutes. Just like when you sweep the floor, it just does a few sweeps and moves forward all throughout the 20 feet. And this is very important because the health of the microbiome is dependent on this. Because if they don't exist, then the microbiome is not going to stay healthy, just like a quagmire versus a stream. So the bacteria will start to grow, and the bacteria from the colon will creep back up into your small bowel that you will hear about it in the small intestinal bacterial overgrowth talk. And these contractions almost happen about 11 to 12 times per minute, and it goes through. So very important. So we're getting to the colon. So now small bowel connects to the colon, and at the beginning of the colon it's called cecum, and this is where the appendix connects. Appendix classically is considered a vestigial organ. That's a concept that is being challenged significantly, and we are finding a lot of work that appendix does for you. So one part of it that we know that it's important is the fact that it can harbor a lot of microbiomes, especially archaea, that can repopulate the microbiome of the colon when it's wiped out. So it can act as a reservoir to repopulate the microbiome in the colon, which is a fascinating phenomenon. Obviously, when it gets inflamed, the classic disease that is associated with it is appendicitis, that if it's severe, that it needs to come out, although the new data is showing that you can salvage the appendix by antibiotics, but that's a talk for surgeons. So the rest of the colon has an ascending colon, transverse colon, and descending colon sigmoid, and then cecum. This essentially wraps around the whole abdominal cavity. So it's a loop around, as you can see on the picture here. So that's why it's really hard sometimes with the GI disorders to see where the pain is coming from, because these are not small organs. They're all over the place, right? So the colon is all around, the small bowel is all over the place, and also the detection of pain in our bowels is not accurate. It's not somatic. So the pain that you feel somewhere, it might be coming from the other side. So it's not accurate. So that makes us a little bit hard to diagnose where exactly the pain is coming from, and we become dependent on tests to see where the source of problem is. How does inside the colon look like? Let me just run this. Alrighty. So that's inside the colon. You can see the vessels, and that's a little bit of a stool, and you can see the vessels, how nicely they're in the colon, and you can see that as we come out. Well, now I have a surprise for you. That was not actually human. That was actually a mouse. So, but it's amazing how GI tract of mammals look similar when we do colonoscopies or endoscopies on dogs, pigs, and also mice. It's quite similar that we see. And that's the beauty of evolution. And in our lab, we do a lot of colonoscopy, so I thought I'd put that up for you to see how that looks. And then the colon obviously leads to the rectum, then the anal canal. And this is an area that is very busy. Multiple vital organs are there: the perineum, the uterus, the bladder, the prostate, the ovaries. It's a very complex area. I'm just going to quickly talk about how defecation occurs. So we have, just to familiarize you with the anatomy. So if this is a cut from the side, right? This is the pubic bone, and this is the spine, and this is the tailbone, right? The bladder sits here. Behind it is uterus and rectum. Obviously, in men, this doesn't exist. And the prostate sits over here, okay? So rectum sits behind this. And then there is a sling that connects to the pubic bone, comes and goes around the rectum and goes back to the other side of the pubic bone. But that gives the rectum an angle, something we call rectoanal angle, that gives us continence. And that's very helpful on top of the external anal sphincter over here. So when we have a bowel movement, this relaxes, the rectum straightens, and the anal sphincter voluntarily we relax it, and stool can go out. But you can see that how many things can go wrong if this complex phenomenon does not occur. So, and that's what we call defecatory disorders. It can be present themselves as constipation, fecal incontinence, inability to push out, straining, and that's one whole field by itself. So this is our team. Obviously, none of the work in our group can happen without the research team and also the clinical team to collaborate. Interesting enough, I was trying to find a good picture that includes everybody, but unfortunately, during COVID times, we don't do group pictures anymore. So I couldn't include everybody, but I just wanted to see that behind all the things that we do and you're going to hear about, there is like 50 researchers and clinicians that help us push things forward. So with that, I'm going to introduce Dr. Mathur. Dr. Mathur is an endocrinologist by trade. But she works on microbiome, and a very cool part of microbiome, how microbiome involves the sex hormones, and how it involves aging, and how it involves diseases that affect our body based on hormones. And this can be, for example, polycystic ovarian syndrome. So she's a pioneer in that field, and very excited to hear about the role of gut microbiome as general, especially in the setting of endocrinologic disorders.
Hi, everybody. So full disclosure, as Dr. Rezaie just said, I am not a gastroenterologist. I'm an endocrinologist. But aside from that, or because of that, I get the most interesting talk, I think. And I hope you all agree. So let me just make sure this works. There we go. So let's start off with a basic question. What is the microbiome? Well, the microbiome is any and all microbes that are in and on our bodies. So they're microbes that are in our mouth, as Dr. Rezaie was talking about, on our skin, in our vaginal flora. So all of these different areas in our body actually have their own microbiome. Now, we used to call it normal flora. That was kind of the medical term. We now call it microbiome. But if you look here on this slide, you'll see the phylogenetic tree of life. Some of you may have flashbacks to biology in high school with this, but you'll notice here that the phylogenetic tree has 3 arms. We usually think of 2. We think of the bacteria and we think of the eukaryotic cells, right? These ones are plants and animals, fungi, and these ones, of course, are bacteria. But there's a third branch here, which is archaea. And archaea were initially grouped together with bacteria, but they're now thought to be very different. And the reason I point it out is because they actually have a specific role in humans. They are the organisms that produce methane. So you're going to hear a lot about that in the talks that are subsequent to this. Now, what you don't see on this tree is viruses, even though viruses are part of our microbiome. And the reason is that a virus really isn't considered part of the tree of life unless it's actually hijacked another organism. So once it does that, its metabolism and it starts to get revved up and it actually has an action. So it's not actually considered part of the original tree of life. So, as I mentioned, bacteria, archaea, bacteriophages, fungi, protozoa, and viruses, all of these live in and on us. And if you look at the data, it suggests that there are actually more microbes that make us than human cells, which is kind of an interesting concept. If you put us in a blender, about 56 of us would be microbial cells versus less than that for humans. So the interesting thing, too, is that when you look at the microbes, obviously the largest proponent is going to be housed in the gut. So even though we do have flora everywhere else, the gut is really responsible for that interaction between us and our microbial world. So I put this slide on here because I think it's kind of fascinating, because we always talk about the human microbiome, but the microbiome actually exists everywhere. And so this is actually a flea. This is an electron microscopy of a flea that was on a dog. And then on this flea, you see a mite. You see two mites. And inside the mite, you see bacteria. So this is the mite's microbiome, which is on the flea, which is on the dog, which is in our house. So there's microbiomes that exist all around us and affect all living creatures. And I think that's really important for us to remember. Okay, so now we're moving to bigger animals. This is a cow. We're going to call her Bessie for the purpose of this talk. So Bessie eats grass. Bessie loves grass. Bessie survives on grass. Bessie cannot digest grass. So she doesn't have the enzyme that you need in her own body and in her own mechanism to do that. And that enzyme is cellulase. She can't break down cellulose, which is basically the structure of grass. So what does she do? She chews and she swallows and she exposes the grass and gives you more surface area. And inside her gut, the bacteria help her break down the grass. And then that goes, cows, by the way, only have one stomach. It just has 4 parts to it. So it goes into the ruminal part of their stomach. She brings it back up. She chews her cud, exposes the grass to more surface area. It goes back down. And she keeps doing this until the bacteria can actually break down the grass so she can digest the nutrition in it. So it's kind of an interesting story where Bessie is dependent on her microbiome for survival, right? So she has over 50 billion bacteria per 1 cc of rumen, which is kind of amazing. And a lot of these organisms produce methane, hence cows, methane, greenhouse gas, etc. So if I take Bessie and I decide I'm going to give her antibiotics and I'm going to get rid of her microbiome, bad things happen to Bessie. Bessie will die because she cannot absorb anything. She will starve, okay? No cows were hurt in the making of this talk. However, if I alter Bessie's microbiome and say I get rid of some of the microbes, but not all of them, so I selectively give her antibiotics, I can make Bessie really big. This is not Bessie, but I can make Bessie really big. So this has actually been used in animal husbandry forever. They've done this for decades and decades, where if you go to the supermarket and you see meat and you see no antibiotics, no hormones, this is part of the antibiotic story. Farmers and husbandry, animal husbandry folks have known for years that if you give low-dose antibiotics to young animals, fowl as well as cows and pigs, you can actually make them bigger. You can actually make them gain weight, and the farmer gets more bang for his buck. So this manipulation of the microbiome has been around for a very long time in all different situations. So let's focus on humans, and let's go back. Let's talk about sort of the history of humans and the microbiome. Way back in the 6th century BC, there was a religious group that was very popular in Southeast Asia, particularly in India, called Jainism. And in the Jaini community, they had a concept of a nigoda. And what a nigoda is it was a organism that was thought to be sort of omnipresent. It was in animals, in our bodies, on plants, and on animals. They were small, and they didn't have a very long half-life. They kind of fluttered in and out of our lives. And according to Mathur, who was the head of the Jainis at the time, these nigodas were actually destroyed by humans. When we breathed in and out, we would destroy them. When we sat, we would sit on them. So Jainis were very passive, and they wanted to make sure they didn't hurt these nigodas. And so as they evolved as a religion, they actually wore masks long before COVID, long before masks were fashionable, to prevent the destruction of these little nigodas. And they actually carried little brooms where they could sort of sweep the dust when they were sitting so that these nigodas wouldn't get hurt. So way back then, 6th century BC, there was this concept that there were things that we couldn't see that were alive and that lived around us. Let's fast forward a little bit, and we go to the first millennium. This is actually a story of a Persian philosopher and physician. His name was Ibn Sina, very popular in Persian literature, and he was considered one of the forefathers of medicine. And his works are monumental and instrumental in progressing science forward. And he wrote many, many textbooks, and one of which was the Canon of Medicine. And in this canonic version, he talks about the possibility that diseases like tuberculosis are actually contagious, meaning they can jump from one person to another. Of course, back then, they didn't know exactly how that was happening, but this concept of communicability and perhaps there being a vector between people started to become more and more popular. And this work actually was seminal in medical literature far through the Middle Ages, up until about the 1700s. So this was kind of a permeable thought that was in the medical community at the time. We then move on to Van Leeuwenhoek. So I'm sure that this name is familiar to some of you. Do you know what he did? Anybody in the audience? He was actually attributed to the one who invented the microscope. So there was a guy named Robert Hooke who did this before, but he kind of took it to the next level. And what you see down here in the corner is actually his microscope. So what he did was he actually put together two small brass plates. They were about the size of a credit card. And in between those brass plates, he drilled a hole. And in between that hole, he put in a biconvex piece of glass. So it was like a little bubble. And based on that, he had a little stick that went on the back of it that he could adjust the length, the focal length of whatever was on that little stick. And he could actually see things. And he did this initially because he was in the clothing industry, and he wanted to look at the fibers of silk and stuff. But then he got curious, and he started to put liquids on there, and he started to put a little bit of blood, and a little bit of spit, maybe some urine, and he saw things that were swimming around in there. And so he was actually the first person to see a microbe. And he called it at the time an animalcule. So an animal that was small enough to kind of be like a molecule, minuscule. So the term animalcule was what was used in the literature. But he was the first one, and he's credited with sort of the start of microbiology. And of course, then we go to Darwin. And Darwin lived in the 1850s where everyone was romantic and everyone had poetry. And so he came up with this beautiful little phrase where he talks about each living creature must be looked at as a microcosm, a little universe formed by a host of self-propagating organisms, inconceivably minute and as numerous as the stars in heaven. So began the modern thought about the microbiome. This is a mural that we have at Cedars. It's in one of our major auditoriums, and it basically goes through Judaic contributions to medical history. And in the middle of this mural, you see this gentleman right here. And this brings us more to the modern age. So we're now in about the early 1900s. This gentleman's name is Eli Mechnikov, and he was born in what is now Ukraine. And he has this wonderful history of being interested in longevity. He wanted to see why people aged and what was contributing to aging. And he was actually one of the first proponents of this sort of concept of the gut being instrumental in human health. And he proposed that something happened in the gut that would cause toxins to leak out into the system, and that would make the human ill. Whether that illness was someplace else didn't really matter. It still stemmed from the gut. And he was a big proponent of yogurt. He was one of the first people to say we need to eat better foods, and his thing was yogurt at the time. And so he was kind of the father of prebiotics, probiotics, FMT. It all started here. And now here we sit, like 100 years later, still looking at that relationship and still trying to sort of figure out what's going on here. So in the 19th century, we became really interested in eradicating things that were bad for us in the environment, right? Things like external infection and external disease was really the biggest cause of death, right? Communicable diseases, that and of course childbirth. So we actually started as a society trying to get rid of things that would cause death. We cleaned our water supply. We didn't know before that we had to do that. We started filtering and cleaning the water systems. we started antibiotics, right, in the 1900s. We know that antibiotics were used, and they were used a lot, and perhaps without discrimination for a time period. And all of this stuff changed not only the external environment and made it more friendly for humans to actually live, increased our lifespan, increased our longevity, but it also started to change our microbial composition. Being exposed to things like antibacterial products, hello, remember 3 years ago? Crazy, right? All of that stuff changed our microbial composition. And there's actually now a school of thought that exposure to these things results in eradication of really important microorganisms, and we may never get those back. Martin Blaser is sort of a proponent of this, and he wrote a book called The Vanishing Microbiome, which is really a fascinating concept that as we become cleaner and cleaner and we do these sterilization practices, our microbiome has changed, and we've lost some very important fundamental microbes throughout the course of human life. And there's a question as to whether or not that's now related to what we think of as modern diseases. Asthma, atopic dermatitis, obesity, type 2 diabetes. Is this somehow related to this modernization that's going on and changes in our hygiene techniques? So when we look at how things are developing in the world of the microbiome, we're now starting to understand the symbiosis that occurs. And our focus has shifted from external pathogens and trying to get rid of those to looking at how our internal microbiome actually affects us. So we're questioning the role of our hygiene, we're rethinking antibiotic use, we're trying to understand what influences our microbiome, what do drugs do, what does diet do, and we're trying to understand how that internal microbiome sort of affects us as the host. So that's where we currently are in our dialogue with the microbiome. So as I'm talking, some of you must be thinking, well, then just tell us what a healthy microbiome is. And I can do that in one sentence. We don't know. So we don't know what a healthy microbiome is, and what's healthy for me may be very different from what's healthy for you, and what's healthy for you, and what's healthy for a child or somebody who's growing up in another country. We really don't know. And our thought process is changing now from thinking just about one microbe and one disease to how communities of microbes actually affect us. We're also starting to think about concepts rather than specific organisms, so things like redundancy and diversity. So if I have a group of organisms that can do one function for me, and I wipe them out, I'm kind of like out of luck, right? But if I have 3 or 4 different communities that can perform the same function, and one of them gets wiped out, I can still survive. I can still do that process, whatever that process may be. And the same thing with diversity. We know that diversity is a good thing when we look at the communities around us and when we look at how we live as humans, right? It's the same thing in the microbial world. When you look at diversity, it tends to be associated with health. So diseases like IBD, diseases like obesity, diseases like diabetes, those are all associated with a decrease in diversity, which is kind of a very interesting concept. So I just told you that we don't know what a healthy microbiome is and how this is going to be a very individual thing based on who you are, what you need, and what diseases you have. But you'll see that there's an incredible amount of interest in the microbiome, so much so that, of course, companies are springing up, people are selling things, products are available. You can put probiotics in your lipstick, you can put them on your face cream, you can eat them, you can ingest them, you can wear them. I mean, it's kind of crazy. So what you see here is the human therapeutic market right now for microbiomes, and it's exponentially going up. And then what you see in the slide beside it is the disease states that are being treated. So this is a therapeutic market size and the estimation of growth over the next decade. There's a lot of things on the market and on the horizon for you guys to buy. Be careful. Buyer beware. Just make sure that you understand what you're getting into when you look at these products. So let's talk a little bit about science. The microbiome inside the human does a lot of things for us, and in turn, we do a lot of things for our microbiome. So on this slide, you see some of the things that they do for us. They help us in our immune defense. As Dr. Rezaie pointed out, they also have other things where they help us digest the undigestible. They produce peptide mediators for us. They help regulate our body weight and our body temperatures. And of course, they produce gas and other byproducts that will be discussed later on by those who know much more about that than I do. and they modulate our immune response and help us make vitamins. So they do a lot of things to make us healthy and keep us happy. And in turn, we keep them warm, we keep them safe, and we keep them well fed. So that's kind of the symbiosis between us and our microbes. How do we get our microbiome? Where does it come from? Well, there's some thoughts that the initial exposure may be with the placenta. What we choose to feed our infants when they're born, do we breastfeed them or do we bottle feed them? That will make a difference. What we choose to feed them when they wean and during childhood, what our own genetics are like, what do we like to harbor, what's our gastric pH, what's the environment that we choose to have genetically, the amount of exposure for antibiotics and drugs when our children are little, Timmy with the ear infection, that sort of story, and where we live geographically. All of these things will play a role in how our microbiome ultimately develops. This is a great study. It's a little bit older now, but nevertheless, I think it gives us a fantastic visual. This is a child up until about 830 days of age. This is birth. This is as the child is growing. Oops, sorry. Whoa, 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 whoa. There. And over here are the microbial species. So what you see here is when the child is on breast milk, the microbial pattern throughout the timeline that he's on breast milk is pretty similar. When the child is weaned onto rice cereal, it changes, weaning the child to table food and ultimately to an adult diet. If you look at the adult diet microbiome and the breast milk microbiome, it's pretty evident that they're very different. So what we feed our children makes a very big difference as to what they colonize with. Now, colonization of the microbiome usually occurs within about the first 3 years of life. And this is a great study that looks at 3 populations in different parts of the world. In Malawi, in Venezuela, this is an Amerindian population, and in the United States. And the color codes are right here. So when you look here at the observed taxonomical units, these are basically markers of colonization of the gut. You can see that as we move forward, most of the gut gets colonized right here within about 3 years or 4 years of life, right? And everything looks pretty similar. All looks good across all 3 of these geographical groups of people. But look what happens as we age. This is an adult population. Again, the US is in blue, the Malawians and the Amerindians are in red and green respectively. And look at what you see. You see a marked division in the types of microbes that we harbor versus those in agricultural, more natural environments. So is this diet? Is it environment? Is it genetics, antibiotics, meds? We don't really know. But something happens here that causes our microbiome to start to diverge. And whether this is a good thing or not is what we are exploring. So what's the evidence for the gut microbiome actually affecting human disease? Well, I'm an endocrinologist. So one of the diseases I study is obesity. And we know that obesity is not a one-size-fits-all, right? We know that there's a whole bunch of things involved with becoming obese. Environment, genetics, meds, psychosocial issues, etc. But let's just make the assumption that we're going to take a look at this one part. We're going to look at the GI microbes. And let's go back to a model here. This is a mouse. I like to name them. So this one is going to be Mickey. Mickey here is germ-free, and what that means is that he is born from a cesarean section, and he's kept completely isolated, and his food is irradiated, and he's not exposed to any germs at all. So he's not a happy guy. He's kind of sickly. He has to eat a lot to maintain his weight. Cardiovascularly, he's not as good as he should be, and his immune system's kind of not so great. So he's not a terribly happy mouse, completely germ-free. So let's give him some microbes. So let's give him and expose him to the fecal flora of a healthy mouse. What happens to Mickey? He gains some body weight, his heart rate slows down, his immunogenicity improves, he gets a little bit more healthy. He looks really good. So let's take it one step further, and let's give Mickey the fecal material through a gavage and colonize him with microbes from an obese mouse. Mickey gets really big. No mice were harmed in the making of this lecture. Mickey gets really big. And this is an interesting concept here where we know that obesity can actually be a transmittable disease. So what does this show you? This shows you that the microbiome can affect the host phenotype And it also shows you that it might be able to transmit a phenotype, which is so fascinating. And all of this sort of animal work and stuff has led to multiple, like large grant-funded consortiums all across the world to try to look at the microbiome. So we've got huge consortiums in Europe, in Canada, and the United States, all trying to decipher exactly what's going on here. And when we look at the literature, we see that the amount of science that's going out based on microbiome work has exploded. So in the last 5 years, there's been over 100,000 papers published on the microbiome, and in the last year, about 26,000. So it's increasing, and there's a lot of data out there. But the question then becomes, what do we do with that data, right? Is that really cause and effect? Are we really showing something? What's relevant? What do we do? How do we decipher this as a scientific community? And how do we pass that information on to you guys so that you make the right choices for your own health? Well, it turns out that it's complicated. And Dr. Rezaie just went through a lot of information about the gut. But let's talk about the microbes that live in the gut. So we used to think that these microbes were just scattered around, right? That we had anaerobic microbes, we had gram-negatives, gram-positive cocci. They were all just kind of all mixed up in the gut. And, we didn't really know how they lived or what they did exactly. But then we realized that it's not like that at all, that these microbes actually form communities, and these communities are actually very intricate. So certain microbes like to be in a certain environment, they like to have certain neighbors, certain microbes have different functions. So you can equate it to a city, and you can think of yourself, well, a city has sanitation workers, teachers, lawyers, doctors, has a diversity of jobs to make that city function. If I did something here and I took all of the teachers in this city and I gave them a cold and they couldn't come into work, I'd be lost if I didn't have substitute teachers, right? So redundancy is also important. So when we look at these microbial communities, that's how they live. They live in these communities that have redundancy and diversity to make sure that these communities can thrive, right? So the infrastructure can be relatable to a city. Now let's take that city and let's put it in different parts of the world. Let's say we've got a city, let's say we've got LA, we've got Paris, we've got Delhi, and we've got Tokyo, right? They will all have the same infrastructure. They'll have commonality with how those cities are kind of put together, but they have different geography, different food sources, different languages, different pastimes, right? They have their own character. Each city has its own vibe. So you can think of that as the microbial communities too, when you think about where they're distributed in the gut. So you can look at this, and as Dr. Rezaie said, the gut is huge, right? We've got like 30 feet of gut within us. And when we break that down, each of those little segments, depending on where you are in the gut, is going to have a different exposure. It's going to have a different partial pressure. It's going to have a different pH. These microbes can live in the different layers of the gut that Dr. Rezaie talked about. Are they mucosal? Are they in the stool? Where are they? And how does that play a role in how they communicate and what they do for us? So it's an extraordinarily complicated topic when we talk about the microbiome. It's not a sort of a monolithic entity. And the GI tract is complicated, right? So Dr. Rezaie went through this already. I won't belabor the point, aside from to say the small bowel is really important. So what we see is all of the stuff that's really cool happens in the small bowel. That's where we absorb our nutrition. That's where we have our incretins. That's where the bile comes in. It's kind of the most active part of the bowel. And the stool is really formed in the last 3 to 5 feet, right? So when we think about the small bowel, and if we iron it and we flatten it out, it's the size of a tennis court. There's a lot of stuff that can go on there. But when we think about how the literature reviews the microbiome, they basically do it mostly with stool, and they use stool as a surrogate. So the question is, can stool actually represent the entire microbiome milieu of this 30 feet of intestine? And that's something that we at Cedars are looking at right now. So we consider stool as kind of like going through someone's garbage, right? You can see the leftover takeout containers, the Grubhub. You can find all that stuff, an empty prescription of Tylenol. You'll find all that stuff in the garbage. But it's not the same as going into somebody's house and opening the fridge or opening the medicine cabinet and seeing kind of how they truly live. So we equate the stool to looking in the back in the dumpster, and we equate the small bowel to actually opening the fridge and looking in the cupboards. And when we take a look at the publications that I just talked about, I told you how prolific the field is right now. Less than 500 of the 26,000 papers that were published in the last year looked at the small bowel. So we feel it's sort of an undervalued, underinformed area that we need to look at. So over at Cedars-Sinai in the MAST program, we have a project that we do. It's called the Reimagine program. And essentially what we do is we take subjects that are coming into Cedars for an upper endoscopy, and we analyze the aspirates. So we have a wonderful team of GI docs that do this for us, some of whom will be speaking today. And they collect small intestinal biopsies and aspirates for us. And by looking at this and comparing it to some of the blood that we collect, the questionnaires, the medical records that we can look at, as well as for stool, we can fingerprint these subjects, fingerprint quote-unquote microbially, and start to compare it with diseases. So suppose we have patients that have a rheumatologic disease. We can start to say what is different in the microbiome of the small intestine in people that have that disease. What's less, what's more, what's aberrant, and what can we do to try to infiltrate that and try to kind of fix that process? We can try to personalize this approach, hence the term personalized medicine. And to date, we have almost 800 subjects that we have cataloged and that we're looking at right now. So, as you're now well aware, the small intestine consists of 3 segments: the duodenum, the jejunum, the ileum, and then, of course, the large intestine follows. And so what we found when we looked at the microbiome of the small intestine, we've looked at these particular segments, duodenum, jejunum, furthest distance, which we're assuming is ileum because these are done by endoscopy, and large intestine, which is stool. And this is sort of a topographical map of the microbiome that we see. Each of these colors represents a cluster of microbes, a specific type. In this case, it's at the genus level. And you don't have to know what they are, but let's just look at the colors, right? So here in the stool, we see a lot of green. We hardly see any green in the duodenum. Here, we see a lot of purple. Hardly any purple here. So just by looking at this sort of topographical map as we descend down the intestine, we can see that the profile of the microbes that are here are very, very different proximally to distally. So this is why we think looking at the small bowel is so important. So I've taken you through a journey where we started off 600 BC, and we've kind of arrived to now, like today, which is kind of fascinating. And what we want to do is we want to start to look specifically at diseases that are related to what we think is the small intestinal microbiome. And these are some of the areas that we're exploring at MAST. We are looking at the relationship between hormone therapy and how that alters a microbiome, age and the aging process. We're looking at androgen production and testosterone production, differences between the sexes, because believe it or not, males and females eating exactly the same food have a different microbiome. Obesity, diabetes, we're looking at cortisol, growth hormone. You'll hear about SIBO and EMO here a little bit later on, rheumatologic diseases, and we're also looking at fatty liver. So we have a lot going on, and we're hoping that, as we add on to this chain of interest over, the millennia, that we'll be able to contribute to some answers as to how the microbiome affects these particular diseases. So with that, y'all can take a screenshot of that if you like. This brings you to our MAST website, and you're more than welcome to come on. We have links to some of the papers. We've got some interviews and some YouTube stuff on there too. You can see our handles up here. You're more than welcome to join us, follow us, and we'll do this journey together. Thank you so much for your time. So I'm going to introduce Gabby. Dr. Gabby Leite is our senior postdoctoral scientist at MAST, and she is responsible for a lot of the work that we're doing there right now. And she's going to talk to you a little bit about how we actually look at the microbiome, what are some of the tools that we use, and kind of the analytics that we do. So I'll bring her on up.
Hello, everyone. Good morning. Thank you so much for joining us today. And actually, my lecture is going to be a little different. I want to bring you to the lab with me. I want to show you what we do in terms of clinical analysis of samples that come to us for microbiome studies, and also a little bit more of how we do research as well. Right, so I will walk you through to the entire process from sample prep to the results. even showing a few reports that sometimes we release that may help you in the future to understand how this microbiome is actually reported to you and why it's important. Right, so actually I divide this lecture in two blocks. So the first part, we are talking about the clinical perspective of the microbiome assessment. And with that, I will show you how we isolate and identify potential microbes that are disruptor of the small bowel microbiome or even fecal microbiome. Right, and then later on, we will walk you through a little bit of more broad range perspective and research likely type of techniques that we apply in the lab that usually we use high throughput technologies where we do DNA sequencing and pathway analysis to understand these microbiomes. Right, but first, with a single slide, I want to show you why actually we had to develop all these techniques and why we need to employ these pipelines to study these microbes. So Dr. Mathur just showed you very beautifully what is the microbiome, right? So the microbiome is a mixture of different types of microbes all together interacting. So we are talking about bacteria, we are talking about fungi, we are talking about archaea, even parasites that interact together in a specific site. And all these microbes, with a few exceptions, they have one thing in common. They're very small, right? So we cannot see them with the naked eye. And because of that, it's very difficult to isolate and identify these microbes. So that's why we need to do more research. We need to create techniques in order to do that, right? Including the clinical side. So we don't just get a sample in the lab and give you right away a result of what is there. So we need to employ some techniques, and this is exactly what I'm going to show to you today. So basically, we have one goal in the clinical lab, and one goal only: isolate and identify microbes. We want to know if these microbes are disruptors of your small bowel microbiome or fecal microbiome or any microbiome that we are studying. And there is only one way to do that: by isolating them, by identifying them with specific techniques that can be a biochemical test, can be a protein analysis, it can be a DNA sequencing, it doesn't matter. We need to identify this specific pathogen, right? And then, because of that, is when we can release the report and understand better how these microbes are interacting with your normal flora, with your microbiome. So first things first, I want to walk you through since the sample collection throughout the microbe identification. So we receive samples in the lab. What we do first, we give a quick look in fresh samples. We want to see it, what's going on under the microscope, right? So in order to do that, we need to employ a few techniques, right? They are not exactly easy to visualize, but we can do a few things to do that. And one of the things that we do is a staining technique. Some of these microbes, they can be stained. You can use a mixture of colors so you can see them on the microscope, and that actually gives you a little bit of information of who they are, right? So we employ grand stain technique, and we observe them on the microscope, and then that give us a direction what should we do next in terms of growing them and identifying, right? So during these staining techniques, usually we see two types of colors on the microscope. We see what we call gram-negative microbes, and these are very important. I bet you heard a lot about them before. So these gram-negative bacteria, they're usually involved with infectious disease. They're usually involved with conditions such as small intestinal bacterial overgrowth, and we can actually see them on the microscope. So you can observe that they have red colors, they have a specific shape. In this case, it's a bacilli shape, right? And then on the other side, we can also see microbes that stain in purple. We call these gram-positive bacteria because they're purple, right? And then they also have different shape. So in this case, they're cocci shape. Sometimes they live together as a pair. Sometimes they live together like a grape, like grapes, right? So, and then this is the first step in what we should do in the lab in order to define the next steps. And then during this step, as I just mentioned, as we are visualizing your samples on the microscope, we can already take a few information about these microbes. One of the things that we can't see it is how they look like. And this is very important to us. It's like understanding their shape, if they have a bacilli shape, like this one, if they have a cocci shape, like this one, or the Y shape, we will define what to do next. And a lot of these shapes are associated with specific pathogens and give us some information like, okay, it's potentially a Escherichia coli. If it's a bacilli, that I see color as red on the microscope, depending from which site we collect these samples, right? And then we move on for the next step. So after we visualize these samples, we still have a lot to do. That's just the beginning, right? And then one of the things that we need to do is search for other microbes present in a specific sample. So we are not only, again, in a microbiome environment, only to bacteria. Although most of the research that we do these days is mostly on the bacterial side, let's remember that these microbiome have other types of microbes as well, such as fungi. And we see them all the time, even under the microscope. So we see fungi such as Aspergillus here, and this is a beautiful structures that we can see under the microscope, which can almost already tell you the species that is dominating in a specific environment. Or in this case, Candida albicans. And Candida albicans is a very important microbe, especially in the small bowel. It's one of the most important ones and associated with patients with small intestinal fungal overgrowth. Right? So then, after we search and we can see what is the majority of the microbes in a specific site, we can do what we do the best in the lab. We need to culture these microbes for further identification. And culturing these microbes involved a lot of steps, right? So the first step we already took. We know how they look like, we know their shape, so we know what to do next. How we know what to do next? Because depending on their shape, depending on their color in a grand staining, depending if they are fungi or if they are bacteria, I can select specific growth medium to make them grow in the lab in a way that I now can see them. So the goal during this step is grow these microbes enough to a point that I can see them and I can apply specific tests for identifications, right? So then I have a few examples of growth medium that we use in the lab, including the McConkey agar that we will talk about it, that we usually use to diagnose patients with small intestinal bacterial overgrowth. We also use the blood agar, where we can grow more fastidious microorganisms, some of them also disruptors of the microbiome, such as Clostridium difficile, such as, although we will not speak about this today, but Lactobacillus potentially as well. And we have another agar over here that is mostly for fungi, that is the Saburo agar, that we can grow Candida albicans, right? So after receiving the samples, we took a look. Now let them grow on this specific medium and take into consideration a lot of characteristics of these microbes. If they like oxygen or not to grow, if they need specific nutrients to grow, and we do that, right? So after we got the samples, we plate them on those agars, right, like you see in this picture. And then we incubate them in this incubator where we can control the temperature, we control the pressure, and we can control the exposure to oxygen, right? So we have plates that are completely exposed to oxygen, so we can grow aerobes, like Dr. Mathur just mentioned to you, like we have aerobes growing in the small bowel or stool samples as well. Or you can grow them in these specific jars where we can remove the oxygen content from the environment. And those bacteria that don't like oxygen will start to grow as well. So we do both at the same time, right? And then right after, we'll wait a little bit. Sometimes we wait 18 hours, sometimes we wait 24 hours, sometimes we need to wait even 48 hours, and for a few microorganisms, up to 7 days, right? So, and then what we see right after that, if there is a microbe and with a potential to grow in this specific medium, you're gonna see plates like this one. And this is a very nice example that we have from patients in the lab, right? So We use multiple agar with the same samples from the same patients, and all of these dots over here, they are bacterial colonies. We call them colonies. They came from a single microorganism that was present in a specific sample. So they grew that now I can see it. I don't need anymore a microscope in order to, okay, like there is a microbe growing at this specific site. And they have different colors and different shape, and I will show a few more pictures to you, but all of this information that comes from this step can also help us to identify these microbes. These colors means a lot to us. So let's suppose this agar in the middle, we call hectoin agar. The hectoin agar is an amazing source of nutrients for pathogens, such as Salmonella, that perhaps you already heard about, Shigella, Escherichia coli. And depending on the color that they show on the agar, it gives me already a hint of who they are. So if it's Escherichia coli, it's going to grow orange. If it's Salmonella, it's going to grow green with a black spot in the middle. And that black spot in the middle also means a lot to us, and I will show you why, right? But at the end of the day, this step will give me a lot of information about what is the potential species. I cannot tell for sure yet which one, but now I have enough samples to do and to go to the next steps. But I want to go over a few of the agars that we use in the lab because we use them to isolate microbes that are disruptors of the small bowel microbiome, of conditions that we would talk about today. We are talking about IBS, post-infectious IBS. We're talking about SIBO as well. And all these microbes can be studied in the lab. And one of the agars that I want to talk about is the McConkey agar that I mentioned a little bit. This is a very important step, and this is a step that we perform with every single sample that comes from the Reimagine study, where we need to define if a patient has small intestinal bacterial overgrowth. How we do that? We culture the samples, the asprays that we collect from the small bowel, such as Dr. Rezaie showed to you how we do it, right? And we wait them grow to about 24, sometimes 48 hours. And then we see these little colonies. These are plates from patients, real patients that we have in the lab. And we see these colonies growing. It's like I told you, one colony came from one single microbe. And what we do next, we count them. We count one by one. And then in this case, I count 1, 2, 3. Of course, we have some technology to do that for us when the amount is excessive, but we count them. And then when we realize that this number is higher than 1,000 colonies per ml of aspray that we collected, that sample is positive for SIBO. So this is how we diagnose SIBO in the lab, right? But more than that, during this stage, we can also take a look closer to these colonies, and you can see how different they are. So you see that some of them are pink, some of them are yellow. Some of them glow more than other ones. Some of them are perfect circles, some of them a little bit spreading on the median, right? And this is also give us information about the potential species. So 2 of the species, the major species associated with SIBO, that is Escherichia coli and Klebsiella pneumoniae, they grow pink, like these ones on the McConkey agar, because they use lactose as a source of sugar. And this is very important to us to know that they are using lactose, and they have all the genetic machinery to break down lactose. They do more than that. I will show that to you. And then we have other microbes. They don't like lactose. They don't use it. They don't have the machinery. And actually, in terms of pathogens, those that don't like lactose, they are the ones that we are concerned, right? So usually Salmonella, Shigella, they don't use lactose. They will show in the agar as these little yellow colonies. But then if we have an overgrowth of Salmonella and Shigella in your samples, we are not thinking anymore perhaps of SIBO. We are thinking about something that needs to be treated with antibiotics, right? Perhaps an infection. But in this case, at least in the samples that come from the Reimagine study, we are searching for those associated with SIBO, right? So this is one step. This is just one side of the story. We have other disruptors of the small bowel microbiome as well. So one of the other one that we can see it and we can grow is Clostridium difficile and Lactobacillus. So these ones, they are more fastidious types of microorganisms. They need more. They need nutrients that usual agars don't have it. And this is part of how and why they are so virulent and so, why they are so good as pathogens. So we need to actually use blood to grow them. They like that. So we create these blood agars where there's a mixture of nutrients with actual blood. And that's the only way that these microbes can grow in vitro. And these microbes also, in the blood agar like this, in a culture like this, you can see a lot about of who they can potentially be, right? The shape of the colonies, and even if they have the ability of breaking down the blood, right? And create this shadow around the colonies. We call this hemolysis, right? So the presence of hemolysis can already tell you if some of these microbes have these enzymes that can break down blood, right? Which is very important for their virulence. And we can see that on the agar as well. So for the Reimagine studies, for the perspective on research, we mostly work with these two agars, McConkey agar and blood agar. And the third one that we do, that we are recently doing more research and understanding, is the one that I mentioned to you before, that is the Saburo agar to grow fungi. So it's mostly Candida albicans, but we have other types of fungi, that yeast, that can grow in this agar. But we do that in the lab as well, where these agars, they're very unique because they have components that inhibit the growth of bacteria. And only fungi can grow in it, right? We develop these components that can inhibit cocci, can inhibit bacilli, although in some cases these bacteria can overcome these inhibitors, but there are a few exceptions. But the goal of this agar is to see if there is an overgrowth of fungi in a specific sample, and we see that. And more than that, what we do as well, that for fungi specifically, and only for fungi, there is one agar specifically for Candida that we can employ and use it to do already identification without any biochemical test, any DNA sequencing test. We can already tell the Candida species that are overgrowing a specific sample just by the color that you see in this agar, right? So then we have, in this case, this is the chrome agar, where it only grows Candida, right? And depending on the color, you can see that is a different types of Candida, right? So we have here Candida auris, that is the light blue color, and if it's a little different shape of the colony, a little lighter blue, is Candida albicans, that is the one that we see the most in the small bowel, right? And then if it's dark purple, it's Candida tropicalis. And then if it's pink, it's Candida krusei. And then if it's another shade of pink, but smaller colony, it's Candida glabrata, another important player in the small bowel. So this is one of the exceptions that we have, where actually you can already tell the species just by looking at this, the shape and the color of the colonies, but not for bacteria. For bacteria, like I mentioned before, we need to grow them, we see them, we have a few informations, okay, they are gram-negatives, they are gram-positives, so who they might be, they grew orange in the agar, they grew pink in the agar, or they might be Escherichia coli, they might be Klebsiella, but I cannot tell yet for sure. I need to do more. So what can we do in the lab in order to identify these microbes? And so far, I'm only working with you, walking through the clinical part. I didn't even start what we do for research, right? So we are trying to isolate specific disruptors of the small bowel. So then what we do biochemical tests. So after we isolate those little colonies, and one colony came from a single microbe, remember, we can apply a huge range of biochemical tests with these specific colonies to see what these microbes are capable to do, So let's suppose we have here a range of carbohydrate tests where we can see which carbohydrate they can ferment. And that tells me potentially of who they are, right? So if they can ferment only glucose, if they can ferment lactose, if they can ferment other types of carbohydrate as well. But during these tests, if they ferment some of this carbohydrate, can these microbes produce gas? This is another feature that we need to check in these disruptors. And a lot of these bacteria that grows in this agar, like this one, it's a tube, but with the agar inside the tube, where we get a single colony from that plate, and we stick that single colony inside this tube, right? And then you take a look after 24 hours, and you see this space in the agar. This is gas production. Why this is so important? Why it's so important to know that these disruptors produce gas? So let's remember that, and then you will see that later, that one of the diagnostic tests that we apply for SIBO, besides culturing of the small bowel aspirates, is breath test, right? Why we do breath test? Because all of these microbes, mostly associated with SIBO, they produce gas. And you can see that in vitro. Look at the amount of gas that a single colony produces after 24 hours. They produce hydrogen, they produce CO2, some of them produce H2S. Remember that I told you that that black spot in the colony is important? That black spot in the colony means H2S production as well, is a marker of H2S. Not only that, let me go back. Not only that, even here, this is a black color in the agar, over here as well, and some points depending on the spot that you get in this test. All this black color means a positivity for H2S, right? So then with this range of tests, we can tell if the microbe can metabolize some types of carbohydrate and can produce gas, which type of gas. So if it's black, it's H2S. If it's transparent, it's hydrogen mostly and CO2, right? We can also check if these microbes have motility. This is important. Most of the pathogens, they are able to walk through the gut. So they can walk through the mucus layer, they can walk through the cell layers. They do that. They have the capability to do that, right? And then we can see that on the agar as well. So usually when we stick the colony in the agar like this, and you see that the bacteria is going over the sides of the tube, this means that the bacteria has motility, right? So with this and many other tests that we do in the lab, we can tell the specific species that was involved or overgoing samples. In this case, that we do in the lab is mostly the reimagined samples, right, from patients coming from upper endoscopy. And the other thing that we do as well, not exactly for research purpose, but again for clinical purpose, we have other ways, more advanced ways, to identify these microbes without doing all these biochemical tests. We still need to do the visual inspection. We still need to grow them as we reach single colonies, right? And after that, the only step that needs to be done is getting a single colony and running a protein analysis, a full protein analysis, where you can check the protein pattern coming from this colony. And you can give the identification of these microbes. And this is exactly what we do at Cedars-Sinai in the clinical lab, not on the research lab. So we use this type of technology to identify microbes. We still apply biochemical tests. It is very important, especially to know if they're producing gas, and which type of gas. I also want you to understand that even the same species of bacteria can behave different in a specific environment. So we have Escherichia coli that sometimes produce only hydrogen and CO2, but we also have Escherichia coli that eventually can produce H2S. And that cannot be checked with this type of technology, only with biochemical tests, right? And then the next step would be finally doing identification using DNA. So then we do DNA amplification, and we use specific assays where we can increase the amount of DNA in a specific sample using probes. And those probes are specific to species that I'm searching for, like this one. We have arrays of tests where we can check for several species at the same time. And this is something that we also do in the lab, and especially apply in clinical labs as well. But all of this come with a cost, a huge cost, right? Because it's not always perfect. One of the things is that not every microbe that we can grow in the laboratory. It's not every microbe that we can even see it on the microscope, right? And then let's imagine the microbiome to a more broad range perspective. We are not growing every single microbe present in a sample, just some of them. So this is the major challenge that we have in the clinic. So how we can actually expand our knowledge, and instead of studying single microbes, which are important as well, how we can study the whole microbiome altogether. And this is what we do at MAST. Right? So we, instead of studying single microbes, although we apply these techniques to diagnose SIBO and SIFO, we apply cutting-edge technologies, high-throughput technologies to study every single microbe in a sample. So we are not isolating one, we are isolating all of them at the same time. And how we do that? So, and then I will walk you through this process. So now we left the clinical perspective of this lecture and going a little bit more over the research perspective, although we have companies these days that already offer tests to check your microbiome in the clinic as well. So that's why by the end of this block, I want to show you a few reports, because if by the end of this block you know how to read these reports coming from these companies, you understood everything that we have been talking about right now. Right, so to a more broad range perspective, to a more research perspective, what we do. We collect the samples from the small bowel, from stool, from any other site that you want to study the microbiome. We have a mix of cells, mix of microbial cells, bacteria, we have fungi, we have potentially parasites, lots of viruses all together. What we do next, we extract their DNA, because the DNA is the code that every single microorganism have it, and that code is unique to them. So this is a bacteria, one example, and this is the DNA that every bacteria has it, right? So then what we do in the lab, we need to break down this portion that's not DNA, and we do that, and we isolate the DNA first. So this is the first step that we apply in the lab. We isolate this DNA, but not only for one bacteria. We isolate the DNA from all of them at the same time, all mixed in a single tube like this one. And then after we do that, we apply or we employ our cutting-edge technologies or sequencers, and we sequence every single DNA in a specific sample. And we can do that in several ways. So I will show you what we do and what we are actually more available to you in terms of research, and what we have been doing now up to these days, right? So most of the microbiome studies, they use 16S sequencing to sequence all the DNA present in a sample, specifically bacterial DNA. Now let's talk about more about bacteria specifically. And why we do that? So although, like I said, every single bacteria has its own DNA that is specific to it, they have specific regions in this DNA. Let's suppose this is a DNA from the 16S gene of a bacteria. They have specific regions, the white ones. They are exactly the same between all bacteria. And then they have the yellow parts, where these yellow parts are the ones that is different between species. So then when we sequence all this DNA together, we can design probes that these red marks over here, where they will cover a little bit of the white part. So I am amplifying my DNA from every single bacteria. That's the guarantee that every single bacteria is going to be part of my pool. But I'm also amplifying the yellow part, where it will bring me information specifically about species identification. And we do that, right? And then we do something very similar to fungi, but instead of using 16S, we use another component of their DNA that we call ITS, but it's basically the same. In a single sample, we amplified specific portions of the DNA that are common to all fungi and some specific spaces in this DNA that are specific to species as well. And then what we do after we sequence all of them, we run a lot of bioinformatic pipelines. We bring all these samples, all this information to the lab, to our computers, and we start to apply different pipelines for bacteria identification. And we have two goals mostly for that. We want to check specifically for diversity, and Dr. Mathur already mentioned that diversity is an important feature of the microbiome. We want to know how diverse is the small bowel microbiome, how diverse are the stool microbiome. And the second thing that we do is profiling, right? So then I will show you a little bit how we do it so you understand a little bit of these terms, because this is something that usually appears in the reports from these companies that provide these microbiome studies in stool samples. So diversity means that after I sequence the DNA, I ran all the pipelines to identify this DNA, match them with a database, identify the microbes that are present in a sample. I want to know how many types of microbes exist in a sample, and this is diversity. So each of these ones over here, the red ones, the purple, the green, they represent one type of microbe. So then the diversity of this environment, in this case the gut, right, is measured by checking how many different microbes I have in a specific sample, right? And then let's suppose that in this sample, I will consider this diversity at this specific point. Now, if I remove one microbe, so let's pay attention on the red one. If we remove the red one, this environment does not have this red microbe anymore. So the diversity decreases. And because it decreased, because now it lacks that red microbe that was present before, now our diversity is over here. There is a decrease in diversity. And overall, what we want for a healthy microbiome is a balanced diversity or higher diversity, which means that you have a different type of microbes collaborating, balanced together, working all together to maintain your body, to maintain your basic functions for digestion, for immunity, right? But then what happens if we substitute that red microbe by a green one? Our diversity is back, right? Then we can compare the sample 1 that had the red one with the sample 3 that now have the green one. They have similar diversity, but they don't have the similar microbiome profile. Because the first one, it was the red one over there, and now our third one is the green one. So that's why the second most important step in microbiome study is the profiling as well. So not only checking diversity, right? We want to know exactly what is there. And then when we do that, the way that we do that is applying all those pipelines where then we organize this data. We organize these microbes by their types, if they are by their abundance as well. It's important to know how many we have of each one in a specific environment. So we separate them like this, but by bioinformatics, right? And then after separating them, we apply different platforms where we can actually classify these microbes. Okay, these ones are Escherichia coli, they are from the family Enterobacteriaceae, they are from the phylum Proteobacteria. Okay, these ones are Staphylococcus, so they have a specific family, they have a specific phylum. So we do that, and because we know this information about all of these microbes, and they are present in a specific database, we can now understand the reports that we get, right? The charts that we get representing this microbiome. So basically, this representation of the small bowel microbiome that Dr. Mathur showed to you is just what I just mentioned to you. It's separating these microbes by different types. So let's suppose this green one might be this green one over here, and also take into consideration how much they take from a specific sample. From this microbiome, the duodenum, this case, the green microbe over here takes almost 56% of all microbiome present in that specific site, right? And then you check the blue one, the green one. Let's check who is the green one. This one, the first one, was from the Streptococcaceae family. And then we have a second one that is the light blue one, that is from the Veloninacea family, right? And then I can see who they are, and I can see how much they take of this microbiome. The report sometimes comes to you as a pie chart, on the other hand. So let's understand these pie charts as well, because this is a just different way that we organize the microbiome data. So again, we separate those microbes based on who they are and how we can classify them, and we organize them in a pie chart, taking into consideration their taxonomic classification, right? So in this type of pie chart, we have information about the phylum level, we have information about the order, the class level, order level, family, genus, and species as well. And this is exactly what comes in your reports when you send your samples for microbiome analysis. And that's why it's so important to understand. Meaning that if I'm checking for a microbe over here, let's talk about Klebsiella, the one involved in SIBO. So Klebsiella is right here. Klebsiella pneumonic, that's the species, that comes from the genus Klebsiella, all the way to the family Enterobacteriaceae from the phylum Proteobacteria, right? So this is how we organize the microbiome data. And this profile is unique to every single person, to every single microenvironment. But we can also plot this profile in a specific graph like this that gives information about how your microbiome is similar to other microbiomes. So if my microbiome, let's take into consideration the gastrointestinal microbiome over here. If I am this dot over here, if someone has a microbiome very similar to mine, that person dot is going to be over here as well. So this graph actually shows how the microbiomes are similar or different. And this is exactly what you're going to see in your reports. So I'm not advertising any company, but I want to show a little bit of this report so you understand. But the first page in the report for microbiome analysis on the clinical part, although we don't use that for diagnostic purpose, right? Just mostly for research, is showing how the microbiome looks like in terms of diversity, in terms of profile. It compares your microbiome to the diversity of the overall population, saying, look, your microbiome is over here, and this is the overall population microbial diversity. Also compare how similar is your microbiome to the overall population. Your microbiome is over here, the profile, and this is the whole US population. This is fecal microbiome analysis. They also give you these pie charts. They also show you what is represented in your sample at specific taxonomic level, at phylum level. This is your microbiome, and this is the population microbiome in the United States. And then they show you what is the percentage of each of these phyla in your sample compared to the entire population. So this is how you need to see through these reports. And they do that even at a more deep taxonomic level, such as family level. But the basic is the same. They compare the abundance of a specific family in your microbiome to the population. And we can extend that to many other types of microorganisms as well. We can do that for fungi, for parasites, for viruses. But at the end of the day, it's always the same information that we are combining all together. We are searching for a specific species, and we are understanding how this microbiome collaborate between them, right? And this is what we do right now. Instead of you only checking bacterial composition of the small bowel microbiome, we search for other types of microbes there as well. Again, remember, when we extract the DNA, we extract the DNA from all of them, not only from one microbe. And we can also employ different types of cutting-edge technologies to give us information about all of them at the same time. But as compared to any other test, we also have challenges. All of this is only possible if we have databases where these databases provide us the information of the DNA information of these microbes. Without having this database, we don't know what we are doing, right? So we isolate the DNA, we sequence the DNA, but we have nothing to compare. If we have nothing to compare, we cannot identify these microbes. So this is one of the major challenge in terms of high throughput technology, and also a lack perhaps of how this microbiome should be reported and analyzed. So that's why sometimes it's so confused to see all these manuscripts and papers showing microbiome analysis from one population, from another population. Sometimes they use different pipelines, and you don't know how to compare them. But it's something that we are working on, and that's going to change in a very short period of time. But what I want you to take with you today is that although we know that we have imperfections in how we access the microbiome, we are pretty good already, right? So we know how to identify these microbes, and we know how to report them to you. And this is what is important to us right now. Thank you very much.